Good morning, AP Physics students. We're going to be trying out some video lessons this week. Also, we're going to be doing some video office hours, those are optional, but it's kind of like Twitch, where I'll be online and you can come by and ask questions and talk to each other. So it's Google Hangouts is what it is. There'll be more information in an email, and also there's just a link on E2SD. It's going to be Tuesdays and Thursdays from 10 to noon. And then also Fridays is supposed to be for my elective class, but I'll let you guys come and ask questions there also. And why not? I'll be online anyway. So that seems fine. But obviously, if they are asking questions, I'll prefer them. Um, Anyhow, we're gonna hop right into momentum because I got that announcement that apparently electricity and waves are not gonna be on the AP test. We're not going to cover those anymore, and we're not going to put them on the final, but we're just going to head right into momentum for now, so we can make sure we start learning what we do need to learn. The last topic, momentum. We're starting off with a car crash. It's a 2,000 kilogram car. It's going 40 meters per second, about 70, 80 miles an hour. It's going to hit a wall. It's going to come to a stop in 0.5 seconds. It asks you to determine the force on the car and then it asks you to do the same calculation if the collision takes more time, 1.5 seconds. And then also it asks you to compare the forces on the 80 kilogram driver inside of each vehicle. Obviously, so if you are just seeing this the first time, hit pause because I'm going to head right into the answer. When you're done solving it, hit play and we'll talk about it. Okay, so what we're using is F equals ma. I didn't even really mention how to solve it, but there were some hints written there. If we're dealing with a force, that's the only tool we really have. Force equals ma, and so we have the mass of the car and the information I gave you about 40 meters per second in 0.5 seconds. Well, that's enough to calculate an acceleration because the final is 0 for velocity and the initial is 40. So it actually undergoes, let me grab my highlighter here. It undergoes a deceleration of 8 g's or 80 meters per second squared, and we use F equals ma again, or for the first time, sorry, we have that 80 acceleration multiplied by 2,000, and yeah, 160,000 newtons. Now, I think my video is probably blocking this answer down here, but really doesn't matter because what we can see is that by increasing the time of the collision, acceleration dropped down to about a third of the original value, or exactly a third of the original value. And so when it comes to the final force, we have a third of the acceleration, so we're going to get a third of the force. So the answer is the 160,000 divided by 3, or what's really interesting about it is that it went down. So same car hitting the same wall at the same speed, but if the collision takes more time, the vehicle suffers less damage. Same thing with driver. The person in the vehicle who had a mass of 80 kilograms, he suffers 6,400 newtons of force if he undergoes 8 Gs or 80 meters per second squared of acceleration. But the vehicle that only suffered an acceleration of 26.67 meters per second squared, or 2.6 Gs, 2.6 times Earth's gravity, G, much lower number of newtons, a third. So what we can see is that it's not how fast you're driving that kills you, it's how quickly you stop. And that's kind of the theme of a lot of car safety equipment. So let's go into our physics content first. And so what we're talking about here is impulse and momentum. So starting on the side of this screen up here, F equals ma. That's the formula we just use to get the answer. If you take acceleration and turn that into change in velocity over change in time, and then kind of multiply both sides of the equation by delta t, those delta t's will cancel out. Those will go away. I'm going to go ahead and let's grab ink and scribble that. So those cancel. And then what you're left with is force times delta t equals mass times change in velocity. And these have names. Mass times velocity is momentum. So over here, what is momentum? Momentum is your mass multiplied by your velocity. It's kind of a seemingly random quantity. But one thing you'll note is that apparently it's conserved, meaning that your mass times your velocity before and after in collisions is the same. Well, why is that? Well, it's because of the other half of the equation. Momentum equals impulse, or should I say change in momentum equals impulse. Impulse is force times delta t, and it is interesting because it is equal to the change in momentum. The force that we're talking about here is the force on both vehicles, and due to Newton's third law, both vehicles experience the same force for the same amount of time. So both vehicles experience the same change in momentum during a car crash, which is why we can say that momentum of a system is always conserved. So both vehicles during a car crash, they feel the same impulse and the same change in momentum. Well, then why don't all vehicles fly the same way? Well, just because you have the same change in momentum, that could be a very high velocity of a low mass or a very low velocity of a high mass. So you could think about a motorcycle and an SUV. Here's your motorcycle and here's your SUV. They can have the same momentums, but different velocities. And so units are kind of interesting here. Momentum has units of mass velocity. So that's kilogram meters per second. So those are the units of momentum. It's kind of covered up down here, so I'm redoing it again. This I didn't know about the video in the corner. Not all the other lessons. I'll get rid of content in the corner. Impulse J, which I sometimes see written as I. Impulse is force times a time. It has units of Newton seconds. So Newton seconds, those are the same. Newtons are kilogram meters per second squared. So newtons are actually kilogram meters per second squared. And you multiply that by the second, they turn into kilogram meters per second. So they have the same units, which they need to because they are literally equal to each other. And so, sorry, it's a little dark here. So interesting units. So you can use both. You can say that it's momentum has units of Newton seconds or kilogram meters per second. It really doesn't matter. I'm going to go ahead and erase this actually though. And then the original slides, the information that's in the corner is visible down there. Okay, videos are not going to play, I don't think. Nope. But that's fine. You can watch them. I'm uploading 2 versions of the lesson. There's some YouTubes in here. It's crash dummies. No, no actual people, just crash dummies. But really, really good examples of why you should wear your seatbelt. And also, here's a big one: is a lot of people have no idea that this is a safety feature and not a comfort thing. A lot of people just shove it down because it's not comfortable and they just don't care. It's actually for during collisions. It's designed to keep your head from snapping off your neck, kind of. And so it needs to be set to the correct height. So there's some cool videos showing some crash dummies and how that kind of affects things. And so all of these car safety devices, you can't change the impulse. You can't change the change of momentum during a crash. Your car is going 40 meters per second. You're hitting a wall. But what you can do is you can extend the collision time. So you can have an airbag and a seatbelt and crumple zones where the car actually crunches instead of the old cars back in the days. They didn't crumple at all. They were made out of hardened metal, and they would just bounce off each other, but all the people inside would die. And so we actually learned that it's a good if your car crumples during a crash, because that is more time to come to a complete stop. And the more time, the lower the force on the people inside of the car. An example problem here: you have a football that is thrown. So we've got a football here. It's thrown, and it's traveling with a speed of 15 meters per second, and then it is going to stop. So it's going to come here, and then it's going to have 0 meters per second velocity. And what is the change in momentum of the football? What is the impulse acted on it? And how much force did it experience? So go ahead and try that and then hit play when you have the answer. Give you a couple seconds to pause. Okay, let's head into the answer. So calculating the momentum, it's important to not get your finals and your initials confused. So final is 0 and the initial is 15. So this change of momentum is as actually negative. I'll get the highlighter out here. So we're talking about over here. Oh, that's not the highlighter. Pen highlighter. There we go. So yeah, final is 0. Initial is 15. Don't forget the mass. So we get a change in momentum of negative 7.5 kilogram meters per second. How much impulse did it experience? The same, -7, but I switched up my units. I'm using the kind of standard impulse units of Newton seconds because yes, impulse and change of momentum equal each other, but an impulse is, let's see if this will work here. Yeah, impulse is a force times a time. So I'm reporting my units out in that manner. Both units would be fine for impulse or momentum. And then C asks how much force it experienced. I can take my impulse equation and plug in the time to solve for force. And then that's that. So your first homework assignment is very much related to this. It talks about just impulse and momentum, and we're not really getting into the car crashes. That'll probably start like tomorrow. We'll talk about actual collisions where we try to figure out how fast objects are moving after they crash. Okay, so you have a homework assignment. We're going to do those little check for understanding quizzes, not every single time, but we will keep rolling with the homeworks that you guys upload with the keys. I'll see you in office hours, or hopefully I'll see you back at South real soon. Take care, guys. Stay safe.